There are 5 methods scientists use to find exoplanets. An exoplanet is any planet that is not in our solar system. The first method we're going to discuss is called the transit method. This method has been the most successful method for detecting exoplanets. This method has resulted in the most number of exoplanet findings. Astronomers have detected 3,294 exoplanets using this method. So how exactly do scientists find exoplanets using this method? It's irrelevant to mention that the word transit means to pass through or across something. And that is exactly what scientists look for. In this case, they look for a planet to pass across a star. When applying this method, scientists first observe the light from a star. If the star has a planet orbiting around it, then as that planet during its orbit comes between us and its star, the planet is going to block some of that star's light that we were observing. So the light from the star will decrease a tiny bit when the planet is in front of the star. And if scientists keep observing the light from the star, after some time the planet is going to move away in its orbit and will no longer be between us and the star. And as soon as that happens, the tiny bit of light that was blocked by the planet will no longer be blocked. So as soon as the planet moves away, we will receive the same amount of starlight that we were receiving initially. So then scientists can know with reasonable certainty that there is a planet orbiting around the star. It's important to note that scientists can't really see the planet itself. So for those of you wondering, why don't the scientists just see the planet directly and not bother with its star's light? Well, it's because the planet is too dim to see directly. I will discuss this more in detail later in the video. Moreover, scientists can keep monitoring that star's light and observe that after equal time periods, the exact same amount of starlight is being blocked as the planet enters into transit again. This will further prove that there is an object that is periodically blocking the star's light, and the only logical explanation is that a planet is orbiting the star. And using indirect ways, scientists can find other properties of the planet as well. For example, when the planet is between us and the star, we know exactly how much of that star's light is being blocked, and so we can deduce the size of the planet from that. If the planet is really big, it's going to block more light, and if the planet is small, it's going to block only a tiny bit of the star's light. Scientists can also deduce how far the planet is from its star. If a planet is really far away from its star, it's going to orbit really slowly, and we can see this in our solar system as well. Mercury, which is the closest planet to our sun, orbits the fastest as it takes the least amount of time to go around the sun. And Jupiter, on the other hand, is much further away from the sun, and so it takes much longer to orbit the sun. So when scientists are using the transit method, they observe that the dimness in the star's light is lasting for a really long time. If they observe that the dimness in the star's light is lasting for a really long time, that means that the planet is taking a long time to complete the part of its orbit that falls between us and that star. And this means that the planet is orbiting really slowly, and we know that if the planet is orbiting really slowly, it must be far away from its star. We can also learn about the planet's atmosphere using this method as well. If the planet comes in between us and the star and blocks the star's light, a very tiny amount of that star's light is going to go through that planet's atmosphere and then reach us. And the atmosphere of that planet is going to absorb the star light in a certain way. An atmosphere that is made out of oxygen is going to absorb the star's light differently than if the planet's atmosphere was made from hydrogen, for example. And so depending on how the star's light interacts with the planet's atmosphere, it can tell us a lot about what the planet's atmosphere is made out of. This transit method can get a bit complicated if the star has more than one planet orbiting around it. If there are multiple planets orbiting around the star's light will get dimmer multiple times. But if two or more planets are blocking the star's light at the same time, then it becomes even more difficult to decipher the number of planets and their relative sizes. The one major restriction of the transit method is that the planet has to be orbiting in the same plane as us and the star. So if the planet during its orbit never comes between us and the star, none of the star's light will be blocked, and so we won't be able to find out if that star has a planet orbiting around it or not. Another method that scientists use to detect exoplanets is called the Radial Velocity method. This method has not been as successful as the transit method, but scientists have found 826 exoplanets using this method. When scientists use this method, they're essentially seeing if a star wobbles or not. Any star that has planets orbiting around it, the gravity of those planets will cause the star to wobble in space. This wobble or movement is super tiny, but it is present and detectable. A star's wobble can tell us if a star has any planets, how many there are, and how big they are. The number of planets can increase the wobble of the star because all the planets are exerting their own tiny gravitational pull on the star. But detecting this wobble is not so simple. The method that scientists use to detect this wobble is called the Doppler Shift. And the best way to explain this is to imagine a scenario where you hear an ambulance siren on the road. As the ambulance passes by you on the road, the pitch of the sound of the siren will change. As the ambulance is approaching you, the siren's pitch will get higher, and as the ambulance passes by you and moves away, the pitch of the sound will become lower. And note that I'm talking about the pitch of the sound, not the overall loudness of the sound. As the ambulance comes closer to you, yes, the sound will get louder, but the pitch of the sound will also get higher. And it is this pitch that we're concerned about. If we were to ignore the volume of the sound and just focus on the pitch, the pitch gets higher as the ambulance gets closer, and the pitch becomes lower as the ambulance moves away from us. Even though the actual pitch of the ambulance siren is not changing. It's not like there is a person sitting inside the ambulance that is constantly changing the pitch of the siren. The pitch of the siren is changing, and the only cause of this is whether the ambulance is moving towards us or away from us. Okay, so enough about ambulances. If we apply the same logic to the wobble of a star, as the star is wobbling, and if during its wobble the star comes closer to us, even by a tiny amount, the light coming from that star will change and become more bluer, similar to how the ambulance sound pitch changed. And as the star wobbles away from us, the light coming from the star will change and become more redder. And it is through this change in light that scientists can detect the wobble. So if scientists are pointing their telescope at a star and the light of the star keeps getting bluer and then redder and then bluer again, scientists know that the star is wobbling, and how much the star's light is getting bluer and redder will tell us how massive the planet is. More massive the planet, more wobble, and more bluer and redder the star's light will get. This method also has a similar downside to that of the transit method. If the planet is not orbiting in the same plane as us and the star, the wobbling of the planet will happen in another direction, and the star's light will not change as much. Hence, there won't be any detectable Doppler shift. More often, this radial method is used for confirming the detection of an exoplanet rather than discovering it. The next method we're going to discuss is called the Gravitational Microlensing method. Using this method, scientists have found a total of 106 planets. This method can be a bit tricky to explain, so bear with me. It makes use of the concept of a bend in space-time as discovered by Einstein. So how does it work? We know that any massive object like a planet or a star can cause the space around them to bend due to their gravity. And any light that is traveling through this bend in space will also bend or curve. So imagine that we're using our telescope to look at a bright star very far away. If between us and that bright star a very dim star happens to pass by, this dim star will be bending space underneath it as it's traveling. And when it comes between us and the more distant star at the back, that bend in space will cause the distant star's light to bend or curve, because the distant star's light will go through the bend in space that the star in the middle created. This bend in the distant star's light will cause the distant star to look much brighter to us than before, because the bend will act as a magnifying glass. But if the middle star happens to have a planet orbiting around it, then that planet will also create a bend in space beneath it. And the light from the distant star will curve by the bend caused by the planet as well. Stars are much more massive than planets, and so the bend in space caused by the star will be much bigger than the bend caused by the planet. So the star will act as a magnifying glass for the distant star's light, but the planet will also act as a magnifying glass. So you have two magnifications going on here. So as the star and the planet move between us and the distant star, first the star will start to bend the distant star's light, and then very briefly the bend will increase by a tiny amount due to the planet. And so the light from the star will also be magnified even more by a tiny bit. And this additional light magnification caused by the planet lets us know that there is a planet orbiting around that middle star. So if we see this sharp peak in brightness, we know that there is a planet orbiting around that star. When scientists are using this method, they're not concerned about the more distant star. Only the middle star is being observed for potential planets orbiting around it. The next method in the list for detecting exoplanets is called direct imaging. This method is still in its initial phase and will become more successful in the future. As of now, scientists have only found 51 exoplanets using this method. So what is this method? As the name suggests, astronomers essentially just take a picture of the star and the surrounding area. At first glance, only the star will be visible in the picture, even if the planet is actually there. And this is because the star's brightness is usually millions of times brighter than that of the planet. So detecting the planet is impossible. So what astronomers do is they have a device, usually in the telescope, that blocks the light coming from the star. And once all the starlight is blocked, all that glare that was caused by the star goes away, and then astronomers can see the really dim planets orbiting around that star. This method may seem random at first, but we apply this method in our everyday lives as well. We're just not aware of it. If you have ever tried to look at something far away on a sunny day, then there is a high probability that you have used this method. On a sunny day, if you're trying to look at something, and if the strong sunlight gets in your eyes, it makes it much harder for you to see that object. So what do? In most cases, you use your hand to block out the sun and then try to view the object you're trying to see. Astronomers are essentially doing the same thing when they install blockers inside their telescopes to block out the starlight. Having blocked the star's light, all the other dimmer objects like planets become more visible. The last method we're going to discuss is called astrometry. This method has been the least successful in detecting exoplanets, as scientists have discovered only one exoplanet using this method. And part of the reason is because this method is extremely hard to apply. When discussing the radial velocity method, we talked about the wobble that stars do as they move in space, which is caused by the planets. In the radial velocity method, scientists were using light waves and the Doppler effect to detect exoplanets. But in this method, scientists just look at the star and see if they can directly see the star moving without any use of light wavelength measurements. Scientists can compare the position of a star against other stars in the sky, and if the distance between the other stars and the star in question changes, and if the distance keeps changing, we know that the star is moving a bit or wobbling. And therefore there is a high probability that there is a planet that is causing it. The reason this method is so hard is because the wobble of the star is so tiny, and if scientists are trying to detect exoplanets from observatories on Earth, the Earth's atmosphere will distort the view of the star. So the star movement is tiny to begin with, and on top of that, if you add the distortion caused by the atmosphere, then it becomes almost impossible to detect and confirm an exoplanet discovery with any reasonable confidence. These are the 5 methods scientists use to detect exoplanets. If you were to take one thing away from this video, I would say it would be to appreciate the level of effort scientists have to apply to discover these new exoplanets. If you guys have any questions, let me know in the comment section. Once again, thank you for watching.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.